Okay, so as we proceed further in this chapter, okay, one of the last things we talked about is why is there more isomers for alkenes than there is that of alkanes? Yeah, you can move that double bond around. Okay, so that's what we're talking about here. For example, butane only has one isomer. Okay, that being 2-methylpropane, but butene is you could say is the parent compound, 2-butene, and then 2-methyl-2-butene would be the second isomer. Okay, so no surprise, you can find the longest continuous chain, change the suffix from ane to ene. Said no surprise there. And for when you go take organic chemistry, the one individual we've got, I don't know if they're always going to use common names for that, but that's what the author goes on to talk about now. For example, the example we gave was you wouldn't say ethine, but you might say acetylene. When you get to the acids, they wouldn't say methanoic acid, they'd probably say formic acid. Those are all common names. So, how many carbons are we talking about with propylene? And ethylene? Well, where's the one carbon alkene? It has to be carbon-carbon bonds. That's right. You got to get up pretty early in the morning to get something by you three, right? Something like that. Okay. No, right now you're so smart, but if it was like 5:30 in the morning, what would it be like? Yeah. Did you like my burnout this morning? I don't know what Mr. Sutton was doing. I thought that's what he was trying to emulate. Okay, tires one ear. Okay, could be. So we've been introduced to this cis-trans isomerism mainly when it came to ring structures. Okay, and that's going to be more important when we talk about these alkenes, and it doesn't quite say it yet, but I want to say this trend started in the 1990s, probably 96, 97, maybe a little later. Uh, bump, bump, bum, bump, bum. I, it's none of my business. Okay. I think you call that. My wife actually got a phone call from her own number. think you call that spoofing? Okay. So, why do you suppose that is? It's talking about this restricted free rotation. Why is it that double bonds can't do that? Well, one way to look at that would be, okay, so when we're looking at these alkanes, okay, you got just a single bond in between them, just like twisting a pin. This has free rotation around there. But the moment that you make a double bond on there, okay, if you had two pens, for instance, I got a pen and a pencil, I get that, you're restricting that free rotation. Because now it's kind of like an equal sign. There is no free rotation, unlike this with that of the alkane. Okay, sometimes you want to look at it like this. Okay, so back to this idea about this isomerism, and I don't think you see this as much as what we said back in the 90s and probably 2000s was, oops, this guy right here, okay? And what that meant was, I still see this from time to time, you may buy a certain set of potato chips or certain brand of snack food, and it's going to say 0 grams of what on there? Possibly. No. Okay, say that again. Yeah, there's 0 grams of trans fat on there. So what that's related to is the idea that fatty acid compound that's on the end, it's like this, okay, pointing in opposite directions rather than both pointing up or both pointing down. Because what does that mean if they're both pointing the same direction? They're cis compounds, but if you're pointing in opposite directions, then you've got a trans compound. That's right. We have problems there, Mr. Tom? You don't have that? Okay, well, I don't think it's the end of the world. Besides, I think we're just going to do one more slide and then go through some examples that I want to go through on these addition reactions. I was kind of hoping to get, that would have been quite a bit to ask it that far. We're just not quite going to make it. Okay. Because I want to illustrate what the difference is between these reactants. Okay. Other than just the name, you get that. So that that third point down, like you pointed out, the presence of weak pi bonds are responsible for high reactivity. So look, it says here, alkenes will undergo a wide range of reagents that alkanes are totally unreactive. What was it that you had to have for alkanes to react? A catalyst, that's right. So if catalysts are not present, they would not react. Yes? Well, there's a couple students standing out there looking inside, and I thought maybe there's problems with the printer or something to that effect. I was going to see if I could offer some assistance. Okay, does everyone have this information? Wants it? Okay. So, and we briefly talked about this last week. And what we're talking about is this, okay? That we know when it comes to some of these reactants, like, just keep it simple. Okay, so what could you possibly throw into? Yeah, you could throw in a halogen, which would be fine. Okay, so upon doing that, if we want that to proceed, what do we have to have? Yes, you better have some heat or some UV light or something to that effect. So let's keep it as heat. And then what we see happening because of that, if I can get the marker off or apart, these two are still there. Go like that. Then that last bond is going to be what? It's going to we're going to put a chlorine on here. And remember, if you wanted to put plus HCl, you can, but most organic chemists don't put that on there because it's not important to the reaction. But if you feel so inclined, it's not wrong. But now, if this reaction wanted to proceed, then you just put another chlorine on here. Now, for these other addition reactions, when it comes to these, if we have, for instance, this instead, okay, so I can't remember how we've, okay, we had this up on the board last week, okay, so when we look at what a symmetrical and an asymmetrical reactant are, okay, what did it say some of your reactants could be? It said halogens. The last thing you wrote down. Water's one. Okay. Now, there's going to be a whole set of reactants that you can use. And what that means, okay, is something is asymmetrical. Okay. Do you suppose that's the same, or is it kind of lopsided? Two sides. Okay. So it means it's lopsided. So symmetrical then would refer to this. You have chlorine atoms on both sides of the bond, or they're bonded together. That is the symmetrical type. I always got to make sure I word that correctly. So we've got chlorine. You could have two I's and bromines. Oops. I need to put the commas in. There's a bond in between them. Now, so an asymmetrical and asymmetrical, that's where it gets so confusing. That's why I like to use the word the. Okay, so the asymmetrical type would be, like you said, hydrogen halides. So, for instance, what might something like that be? Yep. Well, give me a halogen. Okay. Hydrogen halide. Yeah. Yeah. And then the friendliest of all of them. Yeah. Aye. Aye. So what I want you to think about, you remember when you're balancing chemical reactions and you had water. What might be the best thing that you can do to help yourself out? Okay, so if that's how we write this, HOH rather than H2O, is that the symmetrical type or is that the asymmetrical type? Does it look symmetrical? It's got an oxygen and a hydrogen on both sides. Did I misstate that? Yeah, an oxygen and then a hydrogen on both sides of the oxygen. Yeah. Hmm. Okay. But does anyone possibly see the problem with that being the symmetrical type? What are the ions for that? Hmm. Right. Okay. So, Mr. Holt, what does that mean up at college, sitting in a lecture room, and I'm not a professor, I know, but they're up explaining something, and the student goes, yeah, yeah. Does that mean that it's boring, or what does that mean? Is it too early? Why is that? Okay. Okay. You could say that this is hydrogen hydroxide. Really, we know it as water. But with that, okay, it goes all the way um, back to here. Just the idea that this is +1, that's -1. So what that is saying is that you have the hydroxide ion and then the hydrogen ion. It doesn't come apart between the two. One hydrogen will stay attached to that oxygen. So therefore, that is not symmetrical. That is rather asymmetrical. Okay. So what that means, that belongs up there with the hydrogen halides. And that becomes more important when you need to be able to recognize what we call the symmetrical compound with, oh, let me start. The asymmetrical compound with the asymmetrical reagent. Because when we get maybe on your same sheet of paper or one of your vocab terms, there's a certain rule that you need to follow. Find something where it says rule on your vocab sheet. It's a Russian name. I'm sorry. Markovnikov. Okay. So what is Markov? Someone now, I'm serious. You are going to come up. You're really putting a strain on your vocal cords when you keep talking. Okay. It's not that we don't want to hear you. So someone else. What does Markovnikov's rule say? What the author likes to say is, for instance, the rich get richer. Sometimes I think maybe some people think that way, and let them think that way. What have you? So while we got this up here, this is what we would call the asymmetrical compound. Okay, if you're reacting the asymmetrical compound with a symmetrical reagent, Markovnikov's rule doesn't apply. Why didn't you tell me I forgot that? Do you notice that? Oh, okay. But anyway, so what we see happening, okay, as these proceed further, what did this say about how this is bonded? It's a double bond, yes, but it's something that made some of you, oh, that sounds so good right now. Right. These pi bonds are very, very weak, okay? So what that means is if we react that with, let's say, the bromine, this is the difference. If that pi bond is very weak, is it going to take a lot of energy to break it? No. Now these bonds up here, however, are very stable. So will this reaction proceed without a catalyst, do you think, since this bond is so weak? It will proceed without a catalyst. Yes. Okay. So then what you're doing is now you're accounting for everything. Okay. See here, we had that, and that. Okay. Now according to this, we are 2 bonds short. But as you note, this weak pi bond got broke apart from that reagent, and then we see this. There's just only one product that you would form. Both bromines then get attached to there. Okay? However, if you're reacting that with the asymmetrical type, okay, then it's just a little bit different. Okay? And what that means is this. Okay? We'll put it in a different color. Because I think this pathway makes more sense if you see it before we talk about it. Some people may disagree with that, maybe so. But now, someone give me the asymmetrical reagent, any one of them. Okay? That's fine. So what that is saying, again, no catalyst is needed. This is where we're gonna apply Markovnikov's rule tomorrow, is that hydrogen is looking to bond to who already has the most hydrogens. Okay? So what that means then is we still have these 3 carbons over here. That bond has been broken. Okay. Now, 2 more bonds need to be put into there. So according to that rule, then, the hydrogen goes to the bond that already has the most hydrogen. But even though this one has 3, can this have any more bonds on it? No, because carbon can only have 4. We know that. This carbon has 1 hydrogen, okay, and a carbon-to-carbon bond. But this carbon has 2 hydrogens on there. So what that rule is saying is that this hydrogen is going to look for the carbon that has the most bonds that it can possibly make. It can't on here. It can bond here, and it can bond here. But the majority of what we're going to produce is going to be this compound according to that rule. Okay? That is your major product. Okay? Then you do need to be able to write both of them. This is the major one, and then the minor product, you would just flip-flop the iodine and the hydrogen. Okay? But we will proceed with that at a later time. So I would venture to believe that on Thursday we'll assign you your first paper. That'll be due a week from tomorrow, it looks like. So, well, how about that? We're assigning it on the 26th and say it's due on the 24th. Wow, we're good. I think that would be the 1st, October 1st, I think. Yeah, there's only 30 days in September. So, Anyway, we'll continue with this